Now, I am going to discuss about the reactor analysis, the continuation of my previous lecture. Now, we have in the last lecture I try to show you that how we can analyze the reactor, and I told you the reactor basically it can be divided, classified into two types. One is called batch reactor and this is continuous reactor. And batch reactor, we take the material at a time, let the reaction take place, and after the reaction is over you take out the material. In between there is no input and output in the system from the system. But in case of continuous reactor mostly there is a continuous inflow and outflow from in the system. Something is coming in and something is going out from the system. And two type of process we have we came across. One is called continuous start tank reactor and plug flow reactor. And in the last class I tried to point out that plug flow reactor, why it is used for the product inhibition reaction. So today I want to discuss some problem related to the reactor analysis. Now, first problem I want to discuss, that is we are planning to operate a batch reactor to convert A into R, and this is the liquid phase reaction. Stoichiometry is A to R. A to R means 1 mole of A is converted to 1 mole of R, that is the stoichiometry A to R, and the rate of reaction is given. How long must the reaction how long must we react each batch for the concentration to drop 1.3 moles per liter to 0.3. So, we shall have to find out the time of reaction that is required in the batch process. The batch process basically it is like this, that this is the reactor. We take A, and after the reaction is over we take out all the materials that are of the system. So, here the problem what they have done, that they have determined that this substrate concentration, that at different substrate concentration what is the rate of the reaction, because when you talk about the rate of the reaction, that dCA by dt is equal to Q1 into Ca. Now, so it depends on the concentration rate of the reaction. It depends, this is equal to minus Ra. So, this is directly proportional to the concentration. So, here we can see that Ra as that Ca changes and Ra is calculated. Now, so what we have derived the equation, we can remember that T batch is equal to minus dCA by minus Ra. Now, here we have seen that if you plot 1 minus Ra, Ca equal to, then if you have plot this way or that way, whatever this is, that in this problem it might be like this. So, if you like this, then if you take here Ca 0 and then this is Ca. So, area under this curve you can find out at the T batch. Am I right? So, here I can show you in this reaction minus 1 minus 1 minus 2 minus 3. So, it is keep on increasing. Now, 0.4 is 0.6, then after 0.6 it is again that decreasing. So, it is like this, 1 by Ra, that 1 by Ra is decreasing, that this is that means Ra increasing, that initially if you see that Ra is increasing, that as this is the initial substrate concentration, and then again it is decreasing. So, 1 by Ra increases. So, this is the pattern of the curve that we obtain from this particular. If you draw in a simple graph paper we can have this pattern of the graph. And then what we have, so we shall have to find out this CA0 is here is 1.3 and CA that is 0.3, that and we shall have to find out the area under this curve. Now how you can calculate the area? This is like this. If you draw this like this, this is the area of the triangle. So you know the value of this, you know the value of this, you multiply this with this, you can find out the area. And this this is the triangle is half base into altitude. So you can also find out this area, and here also you can find out base. And this room that we have in the centimeter graph paper, you can find out each room what is that correspond to what is the time. So you can do the calculation and find out the T batch. Now we have done this here, that 1 minus from RA we have calculated 1 minus RA, and we plot here. This is the nature of the plot, and you see that this is 1.3 and this is 0.3. So area under this curve we shall have to find out, and if you calculate the area under this curve, it is coming around 12.7 minutes. So you can do it by yourself and find it out that how it can be calculated. Now next problem that we have for the reaction of problem 1, what size of plug flow reactor would be needed for 80% conversion of the feed stream 1000 moles of A per hour, Ca 0 is 1.5 mole per liter. Okay. So what is this? This is equal to plug flow reactor. What is the nature of the plug flow reactor? It looks like this. This is the plug flow reactor. Now what is the initial concentration that we have? This is 1000 mole of A per hour, and whereas Ca0 is equal to 1.5 mole per hour per liter. Okay. Now 20% 80% conversion, that means 20% will remaining. So if you multiply it by 0.2, then Ca will be equal to 0.3. Am I right? And here this will be same. This is now this cannot be same. 100 moles of A will be converted to B, might be. So flow rate will be same. But if you consider here flow rate, that you can find. How we can find out the flow rate? Flow rate you can easily find out that this is the flow rate. How you can find out the flow rate? Flow rate equal to, this is 100 mole of A per hour, and if you divide by the Ca0, Ca0 is what? 1.5 mole A per liter. Am I right? The mole liter and mole liter will cancel, and it will come liter per hour. So you can, and this flow rate will be same. This flow rate, the input and output flow rate is same, and here I told you tau plug flow reactor is equal to what? Tau forward. This is the volume, working volume of the reactor. Then we can find out V by F. This is the tau plug flow reactor. We can we can find it out. Now here what we have done, that we have Ca0 is 1.5 moles per liter. Now Xa is 0.8. So CAF is final is 0.3 as I mentioned, and this is moles per hour. So here we convert it to minutes. If you want to minutes, you divide by 60, we will get the minutes. Now in case of tau plug flow reactor also, we have, it is similar to your expression is similar to your batch reactor. This is minus dCA by minus RA. That is we have here Ca0 to Ca. So this is 1.5 and this is 0.3 that we have, and this we shall have to do the integration like this. Now, and in our previous case that we have already seen, we have the plot like this, 1 minus R A versus C A. Am I right? So, here we have C A 0 and this is suppose C A, and this is equal to 1.5 mole per liter, and this is 0.3 mole per liter. Okay. The area under this curve I can similarly find out, and here it has been determined, and it is found to be the tau plug flow reactor is coming about 17.1898 minutes, just like this. Now, we have already seen that this is equal to V by F, and F I have already shown you how we can calculate. So, if you find out the value of F, the V equal to will be tau plug flow reactor into F. So, you can find out in liter. This will be the liter. This is exactly what we have found out, that tau plug flow reactor by Ca 0, if you divide by this, you will get your volume is coming about 190.9733 liters. This will be volume of that plug flow reactor. Now, third problem is that the same problem. Now, what we are thinking that what will be the size of mixed flow reactor? Mixed flow reactor is similar to your continuous start tank reactor, and is needed for 75% conversion of the feed stream, 1000 moles of A per hour at Ca 0 1.3 mole per liter. So, that we shall your reactor will be like this. Your continuous start tank reactor can be expressed like this. So, there will be continuous inflow and continuous outflow. This is CSTR. Am I right? So, he is saying that input here we have 1000 mole A per hour, and Ca 0 is 1.2 mole per liter. Now, the Ca, this is 75% conversion. So, 75% conversion means this will be multiplied by 1 by 4, and this will become, there is 1.2 into 1 by 4, then 25% will remain. That means, it is coming about 0.3 mole per liter. Okay. So, this is like this. So, here the situation is very simple, and under steady state condition, what is the steady state condition? Because I told you in a continuous system, it is possible that to attain the steady state, how you arrive the steady state condition? If you run the system for infinite period of time, a time will come when the substrate concentration in the reactor will be uniform, and then and only then the steady state condition will reach, and this is possible when rate of accumulation of the substrate is equal to 0, and that is the basic thing that we have. And so, under steady state condition, S is constant. Why it is steady state? How you define the steady state? When the concentration of the different component present in the reaction mixture is remain unaltered with respect to time. In different section of the reactor, it remain unaltered unchanged with respect to time. So, if S is constant, then what will happen? That your rate of reaction will be constant, then your tau CSTR how we can we have already seen tau CSTR equal to what? CA0 minus CA by minus RA. Am I right? Now, what is CA0? CA0 is 1.2, and what is CA? This is 0.3, and at 0.3, if you look at in the problem 0.3, you have the rate. This is 0.5 moles of moles per liter per minute. So, you can multiply by that 0.5. So, you can get the tau CSTR, and this is equal to V by F. Now, here it is bigger. I showed you in the last the how you can find out the F. F is equal to, I can write 1,000 mole of A divided by initial substrate concentration 1.2 mole of A per liter. The mole of A so this is per hour, and per hour we shall have to convert it to per minute, that is divided by 60. So, you can have liter per minute. We can easily calculate liter per minute. After this calculation, then we can find out the volume of the reactor is equal to tau CSTR into F. So, here we did the calculation and we find this is about 25 liters. This is coming about 25 liters. Now, here there is the interesting thing, because we get this is how we can, through analysis we can determine this volume, but graphically also we can determine the volume of the reactor. How we can do that? Minus RA and CA when you plot like this. So, here maybe your CA0 and here might be your CA. So, what is happening that what is your equation? Tau CSTR is equal to CA0 minus CA by minus RA. So, your substrate concentration, so here you have minus RA value, you can easily have, and this is the area, this area is nothing but equal to tau CSTR. So, graphically also you can find out, if you want to, you can multiply this, you can also determine the value of this. Now, next problem is that the repeat part A with the modification that feed rate is double. This is 200 moles of A per hour, CA is same to be treated. Now, if the feed rate is double, what will happen? So, what is the flow rate? I calculated flow rate is the FA0 divided by CA0. Am I right? Now, FA0 is how much? This is initially was 1000, now it is 2000 moles of A divided by per hour, and this is CA0 is about 1.2 mole of A per liter. So, you can divide by the 60 to get per minute. So, you can easily convert. So, what I wanted to tell that when you increase this 200 moles, basically what is happening? Previously it was 1000, now it is 2000, that means flow rate is increased by 2. Am I right? Flow rate is increased by 2. So, so your equation is that you have same value of tau CSTR, same conversion. If you have same conversion, then this is equal to V by F, then V will be what? 2F into tau CSTR. So, basically that if you double this substrate concentration, the previously it was 25 liter, now it will be 2 into 25 liter, that is the 50 liters. So, we can easily calculate the volume of the that mixed flow reactor. You can easily do that. Now, next is that that you can we have solved this, and we have calculated 0.5, and next problem that we have, that repeat part A with the modification this A0. Now, what they are saying that here now here previously CA0 was 1.2, now it is 2.4 mole of A per liter. Am I right? And here Ca is same. They are saying the Ca should be same. Previously it was 75%. Now they are saying no. The whatever converted, that is the final concentration remaining same. But here the flow rate is 1000 moles of A per hour. Then what will be the size of the mixed flow reactor? Then how we can calculate? Then we know this again, we can easily do that, like tau CSTR is equal to what? Ca0 minus Ca minus Ra. So, this is same, this is 0.3. So, this you do not have to change, only this has been changed, this is 2.4. So, you can easily calculate the value of this. Now, I can show you this value is coming about 4.2 minutes. Now, if you know that, then again you can if you want to find out the volume of the reactor, for that you can also calculate that what should be the volume of the reactor. That also V will be equal to tau CSTR into flow rate. Am I right? The flow rate, we have already shown you how to calculate the flow rate. So, you can find out, and this will come as later. Now, here I want to point out couple of things. Suppose in case of CSTR, we want to convert A into B, and we want to produce basis is 100 kg B. Let us assume that 100 kg B moles 1 kg of B. So, you know the molecular weight of this. Let us assume this is glucose to fructose. Let us assume that this is glucose converted to fructose. Now, why we assume that? Here the molecular weight is 180, and here also you have 180. Am I right? Now, question comes that suppose we want to carry out this kind of reaction, how we can determine the volume of the reactor? How we can determine the volume of the reactor? So, for how we can do that? First, you have to calculate tau CSTR. Tau CSTR, how we can calculate? This is S0 minus S minus Rs at a particular substrate concentration, steady state substrate concentration. You can find out that what is the tau CSTR value, you can easily find out. And here you know the initial substrate concentration, that is glucose concentration, you know. So, if you know the initial substrate concentration, if you this is suppose this is the amount of this producing per day, then flow rate you can easily calculate. This is 100 kg B per day. Now, 1 day is equal to what? 1 day is equal to 24 hours. Am I right? And if you want to convert to minutes, 1 hour is equal to what? 60 minutes. So, this hours cancel, day will cancel. So, you can easily convert kg per minute. If you do that, you can flow rate will come as kg b per minute. You can easily calculate. Now, once you do that, then again if you multiply it by this, V equal to F into tau CSTR. You can do that. Now, question comes, what will happen in case of batch process? What will happen in case of batch process? Now, batch process, it is not a continuous process. So, it is like this. You take the material at a time, allow it to react. After the material conversion take place, you here also basis is same, 100 kg B per day. So, same reaction A to B, and we considered this is glucose to fructose. So same 1 gram of substrate give 1 gram of product. So, I can write this produces, this required 100 kg of A per day. Again you can convert into 1 day equal to 24 hours and 1 hour equal to 60 minutes. So, you can easily convert it to kg of substrate required per minutes, you can easily calculate. Okay. Now, T batch, you can find out T batch equal to same equation that we have, minus ds minus rs, you can calculate. If you have a conversion, then you have to calculate this value. But here there is a problem. Here when you do any kind of batch process, we shall have to consider the downtime, T downtime. This downtime contains the time required for taking out the product from the after the fermentation is over, then cleaning the vessel, and then refill the substrate again in the. So, this downtime you have to assume, or you have to find out. The total time T total will be what? T total equal to T batch plus T downtime. So, why it is required? Because I want to find out that how many number of batches per day you have to calculate, and this amount you have to convert not with respect to per day, you have to convert with respect to per batch. Once you have the information that how much product you have to produce per batch, then you can find out easily the volume of the reactor. How you can then if you divide by then you find out per batch how much substrate is required, because let me show you. Suppose you calculate amount of product B per batch. Now, if you so you find out, and from that you find out amount of A required per batch. Now, volume of the reactor is what? Volume of the reactor, amount of A required per batch divided by initial substrate concentration of A. So, this is what this is the amount is kg, and this will be kg per unit volume per liter. So, kg will cancel, this will be liter. So, you can find out the volume of the batch reactor like this. Thank you.